Okay, I am going to record this lesson. So today's objectives, we're going to talk about making and interpreting scatter plots. We're going to write equations for trend lines and lines of best fit, and then use those lines to make predictions. Okay, a scatter plot is a graph that relates two different sets of data by displaying them as ordered pairs. And the examples that you see on the board are all examples of scatter plots. So if you look at the first scatter plot, you can see that the dots kind of form a pattern. They have a general upward trend. We say that this is a positive correlation, because if we were to draw a line through those, kind of right in the center of all those dots, it would have a positive slope. So there's a positive correlation between the independent variable and the dependent variable. So as x increases, y also increases. Okay, next one, we have a general downward trend, so we have a negative correlation. And whatever data was graphed here, as x increases, y decreases. And then on the last scatter plot, there's really not any observable pattern at all in the dots, so we would say that there is no correlation. So if we're graphing information, say we want to know how much gray hair someone has relative to age, okay? Normally, as someone gets older, they get more gray hair, unless, of course, they color their hair and hide it, but naturally they would get more. So something like that might have a positive correlation. Can anyone think of something that might have a negative correlation? Athena?
The hyperness. As you get older, you get less hyper.
Okay. Okay. So maybe we could say as your energy level. So as you're getting, if age were a factor on the independent axis, as your age increases, your energy level might decrease. Good. What about something that might have no correlation? It doesn't have to be age. It could be anything. What would be an example of data? Two types of data that might have no correlation.
Favorite color.
Okay. Favorite color and age.
Sure.
Okay, so maybe age has nothing to do, we graph age on the x-axis, we graph favorite color on the y-axis. There's no correlation, perhaps, between age and favorite color. Okay, good.
Actually makes sense.
No, it doesn't.
I got you, Sam. I got you, Velvet. It didn't. Yeah, it did, because like when you get older, your favorite color changes, but like it's not the same color.
It might change, but there might not be like a correlation like...
Yeah, because when you add
white to the color,
Right.
it's lighter.
Okay, let's look at an example of this. The example is with temperature. The table shows the altitude of an airplane and the temperature outside the plane. What does altitude mean? Yeah, how high it is in the sky. Okay, so altitude is our independent variable. So that's in the first column, or the first row of our table. And then the temperature is the dependent variable. We want to know if there's any correlation between the two. So we make a scatter plot by graphing these as coordinate pairs. So our first pair would be 0, 59. Our second pair would be 500, and then 59.2, and et cetera. So our graph is labeled for us. So I'm going to start at 0, and I'm going to go up to 59 would be, let's say right here. Okay, our next point is 500, 59.2. So I'm going to go here, 500 would be about halfway. 59.2 is not going to look a whole lot different than 59 on our graph. Next point would be 1,061.3, so that would be a little bit above 60. Next point is 1,500, and it's 55.5, so that's going to be probably there maybe. 2,000 goes with 41.6. That's going to be close to the 40 here. At 2,500 meters, the temperature is 29.8. Okay, at 3,000 meters, it's 29.9, so pretty much the same place. At 3,500 meters, the temperature is 18.1, so that's going to be about here. At 4,000 meters, goes back up to 26.2. At 4,500 meters, it goes down to 12.4. About the halfway point here. And then at 5,000, it is 0.6 degrees, so that's pretty much, I meant to draw that up a little bit, my pen's not quite calibrated correctly. Okay, so what kind of a correlation does that appear to have? Positive, negative, or none? Lacey? It has a negative correlation. So we can say that as the altitude increases, the temperature decreases.
That's not true though. Because the first three.
Well, sometimes that will happen. Sometimes there will be, it does go up a little bit, so there's a little bit of variance, but the overall trend of the line is that as the temperature increases, or as the altitude increases, the temperature decreases. But that doesn't mean it's true for every point, because here it also happened, it went from, where we went from 3,500 from this point to this point, it did go up. So there's going to be little ups and downs, but the overall trend is downward. It's like weight loss. I don't know, you guys are young, you probably have never had to try to lose weight yet, but if you're like me, when I'm on some sort of a diet, my weight always goes, it'll go down, and then some days it'll go up, and then it'll go down. And if I look at my trend on MyFitnessPal over the course of months, there's little zigzags, but the overall trend is down. So you can still say I lost weight, even though there were days when you may have gained weight in between the two. Okay, so this one I want you guys to try, so I'm going to pause the video. If you were watching the video, you should pause it and try this one on your own. Okay, so when we're making a scatter plot of this data, for $10 we have a price of, or 2.5 gallons bought. For $11 we have 2.8 gallons bought. For 9 we have 2.3, let's see, one will be here, out in the middle. 10 again is 2.6. 13, 3.3 would be up here somewhere. 5 is 1.3. 8 is 2.2. It's really, really hard to see up here. And 4, 1.1. Okay, so what kind of relationship does the scatter plot show? Liz? Positive correlation. So what could you say to describe it, Liz? Well, actually, our dollars spent are along here. So we want to say it in terms of, we want to start with as the dollar spent increases. Because whatever we graph on the x-axis is our independent variable. That's the thing that affects the other one. So we would want to say as dollars spent increases, gallons bought increases. Now, in this table, they chose to use dollars spent as the independent variable. We could have used gallons bought as the independent variable, and we could have done it the other way. There's no hard and fast rule that says what has to be the independent variable. Some things are obvious, this one isn't. This one you could have done the other way. Okay, what about part B? Consider the population of a city and the number of letters in the name of the city. What kind of correlation would you expect between that data? Sophia? No correlation, yeah. You wouldn't expect there to be any relation between the population and the number of letters in the name. Okay, moving on. A trend line is just a line on a scatter plot that's drawn near the point. So we try to find, sometimes this is also called a line of best fit, which I kind of like that title because it describes what the line does. It's a line that best fits in between all of the points. A trend line is useful because we can use it to make predictions. And there are two kinds of predictions we can make. Interpolation, the word inter means between. So when we are talking about interpolation, we are estimating a value in between known values. So if we look at the trend line that's graphed here, we could make a prediction. There's no point that correlates with 2 on the x-axis. If we trace a line up from 2, there's no actual point there, but we can make a prediction for what our dependent value would be based on an independent value of 2. Extrapolation is predicting a value outside the range of known values. So extrapolation would be, say we want, this graph only goes up to 6. Say we want to make a prediction for when x is 8. What would y be? That's going outside of the data that we have. Extrapolation, it's sometimes dangerous to go too far outside because sometimes, say you were talking about population of a city, maybe some big event might happen like the bubonic plague happened and wiped out half the city. And you can't always predict in the future that population is going to continue to grow or continue to even decrease depending on what's going on because there are often outside circumstances. So interpolation, predicting values in between, is usually more accurate. Okay, let's look at how we write an equation for a trend line. And this is from a biology application. Make a scatter plot of the data at the right. What is the approximate weight of a 7-month-old panda? So we see in this table that we have that gives us the weight of a panda, we don't have an actual value for 7 months. So we're going to draw a line, we're going to write an equation, and we're going to use that equation to make a prediction. Okay, so when the panda is 1 month old, its weight is 2.5 pounds. So that would be a fourth of the way up there. When the panda is 2 months old, the weight is 7.6 pounds. When the panda is 3 months old, the weight is 12.5 pounds. When the panda is 4 months old, it has a weight of 17.1 pounds. When the panda is 6 months old, skipping over here to 6, it has a weight of 24.3. 8 months has a weight of 37.9. 10 months, 49.2. We're almost to the 50, and at 12 months, 54.9. Probably be about there. So this scatter plot looks very linear. Probably should have specified that this was age and this was weight. Now when you draw a trend line, you definitely want to use a ruler. So we'll be using the rulers. I have them in the classroom. We'll be using the ruler a lot for this. If you're doing homework, you don't have a ruler handy. I know in my house we have like 4 of them, but when someone needs one, we can never find it. You can just fold a piece of paper so that you can get a straight edge because you're not measuring anything. So I'm going to do my best to line up the ruler. kind of nice because you can see the dots on top of my ruler on this screen. So if you use a clear ruler, it's a little bit easier. I'm going to do my best to draw a line that best fits these points. Let's see how I did. I think that's probably not the best line, and the reason why is almost all of my points are lying above the line. I kind of want my line to be so that there's an equal number lying above and below. I'm going to try this. Part of it, my pen calibration is off, so where I try to draw the line is where it actually shows up. All right, that one looks better. These dots are almost exactly on the line. I have some below, I have some above, so I'm happy with that line. So that's my trend line. Now we need to write an equation of the trend line, and we're going to do that by just estimating the coordinates of 2 points on the line. It's helpful if one of the points that they give you actually shows up on the line. I think, let me see what I used originally. I used the point 2, 7.6, so I used this one. And then I also used the point at 4, because these 2 points are very close to being on the line. In fact, they probably would be if my pen calibration wasn't off. So I'm going to use those 2 points. You may choose different points. You don't have to pick points that are there. You could say, I'm going to use 10.45 instead. You could pick a point that's just like right here. So it's not around the line because my calibration's off, but you get the idea. You pick any 2 points that are actually on your line. They can be existing points or non-existing. And write down the coordinates for those points. So my first point is 2, 7.6. My next point is 4 and 17.1, which happen to be 2 values that are in my table. How would I write an equation for a line with those 2 points? This is where it directly relates to chapter 5. What do I do first? Athena? Find the slope. Good. So I'm going to find the slope of that line using these 2 points. So my slope would be 17.1. Let me catch up a second. Minus 7.6 over 4 minus 2. And when I do those calculations, I end up with a slope of 4.75. So that's my slope. What form of an equation would be best to use to start with writing my equation? Sophia? Point slope. So I'm going to pick one of these points. I'm going to use the first point. So my equation would be y minus 7.6 equals 4.75 times x minus 2. And then if I distribute, I'm not going to show all my work here because I'm running out of space. I kind of went downward on my paper, and you can do that on yours too. If I work this through and change it to slope-intercept form, I end up with an equation of y equals 4.75x minus 1.9. So that's the equation I get for that line. And it's best really to put it in slope-intercept form because that's the easiest to work with. When you are putting in values, you're making predictions, you're putting something in for x, getting an answer out for y. Okay, so if I want to know how old the panda, or how much the panda would weigh when it was 7 months old, I would substitute 7 in for x. So I would have 4.75 times 7 minus 1.9, and I get an answer of y equals 31.35. I'm going to check my graph to see if that's reasonable. 31.35, I think. I'm going to try to draw this dot in the right place. There we go. This is what I predicted, which is right on the line. So my equation, I think, is pretty accurate. Sam?
You can't just find the average of 6 and 8.
Find the average of 6 and 8. You probably aren't going to get well, let me see how close you would get. You may get pretty close actually to do that. So when you're doing interpolation, you might be able to do some things like that. But to do extrapolation, say we wanted to find out how much the panda weighed when it was 24 months old. You would need the equation to do that. Problem though, while we're talking about extrapolation, if we wanted to find the weight of a panda when it was like 22 months old, do you think that this pattern would still work? Do you think this trend would continue, the slope would continue at the same rate? Think about how, we don't have pet pandas, but we have like pet dogs and pet cats, right? Think about how they grow in the first year of life, and then what happens after that. They're pretty much done. Animals mostly grow, like that first year is like their whole childhood, and then they do go through a little bit of a teenage phase, so there might be a tiny, tiny bit of growth over that second year, but it's not much, it doesn't continue. So extrapolation, when you're dealing with weight, is not necessarily a good predictor. But if you've ever been to the doctor and they plot your growth and they kind of figure out where you'd be, by the time you get to a certain age, they can make predictions about how tall you're probably going to be as an adult, which is always kind of interesting. My kids always sort of enjoy that. And my one daughter was relieved to know that she probably would actually clear 5 feet someday, and she did, so it was somewhat accurate. But it predicts, you know, what your weight's going to be, what your height's going to be, head circumference, all of that, where they expect people to be. All right, the next example, this is the last thing we're going to do today, and you're not going to have any homework. I want you to make a scatter plot of the data in the next slide and try to write a line of best fit. If we have time to compare today, we're going to compare answers and see who has the closest line of best fit that fits the real line of best fit. So you can actually find this out using a computer, which I'll show you either tomorrow or when we come back from break, and we're going to compare who has the closest line.